So I just wanted to put together a quick video on the subject of pull-out shear. And I noticed that many of the younger engineers coming out of college for some reason have a difficult time understanding this concept. And so I took a look at Shigley's 9th edition, which I had on my desk, and I noticed that it's not discussed in the textbook. There are various examples of bolts that are loaded due to torque and preload and clamping load, but this is something slightly different. This is just where you simply screw a bolt into a threaded hole and you calculate how much force is required to simply rip it out and shear the threads between the nutted joint and the bolted joint. So there's a line of shear which is cylindrical between the two, and this calculation will discuss this type of failure, which is typically called pull-out shear. So I'm looking at chapter 8 in the 9th edition of Shigley's Mechanical Engineering Design, which is very common among engineering college students in mechanical engineering, and specifically after page 409. So if you have a copy of this textbook, you can easily follow along. Now it shows you some diagrams as you read through chapter 8. It shows you a side view of a bolt, and it describes what's called the pitch diameter, or the pitch line of the threads. And if you look at the next page, you'll see that the pitch line, or the pitch diameter, is approximately midway up the height of the thread when you look at it radially. So for this example, I'm going to use a 1/4-20 UNC screw. So I'm going to explain some of the data that I'm using for the 1/4-20 UNC screw. The tensile area is 0.0318 inches squared. The minor diameter is 0.0269 inches squared, and the nominal major diameter is 0.25 inches. The data provided, whether it's an SAE bolt or an ASTM A307 bolt, is the same data, and the minimum proof strength is 33,000 psi, minimal tensile strength is 60,000 psi, and minimal yield strength is 36,000 psi. So let's just say that we're using the tensile area of the bolt, because not all bolts have a minor diameter. In other words, they don't neck down the bolts in order to clear for washers, etc. So just using the tensile area and calculating the diameter using the formula A equals pi d squared over 4, solving for d, I calculated 0.201218 inches diameter. Now we don't always know that in a 1/4 inch depth that a full 20 threads are going to be engaged. So I'm using a knockdown factor of 0.95, which is equal to 19 threads instead of 20 threads for this engagement. Now I just roughly want to find the pitch diameter. So roughly speaking, I'm going to take the average between the nominal major diameter and the diameter from the tensile area. So I'm taking 0.25 plus 0.201218 divided by 2, and I'm getting a diameter of 0.22561 inches diameter. This will be the pitch diameter for the calculation. So if I'm calculating the area of this cylinder, then I'm gonna multiply 1/4 of an inch times pi times 0.22561. That's the number I got from the previous calculation of the pitch diameter. And the area that I get, the shear area that I get, is 0.17719 inches squared. Now, the last part of this calculation is just taking 1/2 the tensile strength is going to equal the shear strength. So the tensile strength was 60,000 psi, the shear strength is 30,000 psi. You take 30,000 times 0.17719 inches squared, and the inches squared cancel out, and you get a shear force of 5,315 pounds force. Now there's another way to calculate this pull-out force, which is basically the diameter times pi times the length of engagement times the tensile stress. So to expound on it a little bit, I have pi times the pitch diameter times the percent of threads, which I said was 19 threads out of 20, which is 0.95, times the shear strength times the length of engagement. So using this formula, the pull-out strength is equal to pi times 0.212 from the previous calculation times 0.95 times 30,000 times 0.25, and you get a slightly different number of 4,503 pounds force. Now these numbers have absolutely nothing to do with the clamping strength or any other bolt fastener calculation. It's simply the pull-out strength force. Sometimes it's very important to know this value because you want to compare it to your proof strength or your tensile strength or other types of clamp load strengths or preloads that you might be interested in when you're doing these calculations. And therefore calculating this number is a very important additional calculation that all mechanical engineers should consider when they're doing work with bolts that are under a tensile load. So I hope this was beneficial to mechanical engineering students, and thank you very much from Iron Designer LLC. Have a good day.